Hey everyone, and welcome back again. So in this lecture, we're going to talk about interactions between populations, and specifically we're going to look at two different life history patterns. So a life history pattern is characterized by how long it takes to reach reproductive maturity and to level off, and so reach reproductive maturity and the level of reproductive output that is produced within the organisms. There are two basic types, and the first one we'll look at is an opportunistic reproduction life history pattern. So opportunistic patterns, these are also known as R strategists, and so in general, they are small in size, they mature very early, and they have a very short lifespan. So things like your dandelions are opportunistic. Another example are most insects are opportunistic. When they do reproduce, they produce lots of offspring, and they have very little to no parental care for their offspring. In fact, many will just leave the egg case wherever they're going, and then they just leave in the hopes that the egg case will hatch and new offspring will be produced. And so they've then passed on their genes. And we're talking about insects again. I know much more about insects than I do plants. Then we have the equilibrium pattern, or the K strategist. So in this, the populations typically remain at carrying capacity. They produce larger offspring. They are much slower to mature, and they have a long lifespan. When they do produce offspring, they produce very few. So we're looking at lots of mammals are K-shaped strategists. Humans show this pattern. Birds also show this pattern. So they put more energy into the growth and survival of the offspring rather than producing lots and lots of offspring in the hopes that some will survive. K-shaped strategists are going to be specialists rather than generalists, and so if life is altered, they are more vulnerable to extinction because of this. So what are some factors that can influence population pattern growth? There's density dependent and density independent patterns. So density independent patterns are abiotic factors that affect population size, whereas biotic factors are going to be your density dependent factors. So abiotic factors are going to be things like weather is going to be an abiotic factor. Shelter is abiotic. Natural disasters, abiotic. Whereas density-dependent factors are biotic factors that affect population size. So disease or competition, parasitism, those are all patterns or are factors that influence population because of the number of organisms within the population. So what is competition then? Competition is the interaction between two organisms in which both require the same resource, and that resource is limited. And so the more individuals within a population, or the more individuals within a community, the more competition you're going to see. So I'm going to use this, and this is definitely a joke, but when COVID-19 hit, initially there was almost like a competition to see who could get the most toilet paper. Every single human was stockpiling toilet paper, and so then so I won't say every single, I'll say many humans were stockpiling toilet paper. So then those of us who weren't stockpiling when we went to the store were hoping to find a 4-pack of toilet paper because we were running low. And a lot of times you couldn't find it. So it's kind of crazy. So that would be kind of like a competition, but in real competition, typically you're looking at things for survival. Toilet paper is not really a survival need. It's more of a more developed country benefit because we have toilet paper and everyone gets toilet paper. So competition is a density dependent factor. So the denser the population, the more likely you're going to have competition. Ecological niche is the role in which each organism plays within the community. And so an ecological niche includes habitat in which the organism lives and the interactions with other organisms. So every organism has its own little niche that it's going to fit into. So the competitive exclusion principle states that no two species can occupy the same ecological niche at the same time if you have limited resources. You can't have two organisms or two species that are both trying to get the same food if there's not enough food. One of those species is going to outcompete the other, and the other species is either going to have to leave or they're going to die. And so one way of getting around this is by resource partitioning. So what that does is you can increase the number of niches within one area by partitioning the area up into different resources, okay? So things that might happen is you might have different ways in which resources are utilized. So what this will do is it decreases competition between the species and allows that both species can live within the environment within their own little niche. And so let's look at how resource partitioning might look. Hold on. I thought I had a better picture of this. Hold on. One more time. Aha, here's my resource partitioning. So here we have different warbler birds. And if you look within one tree, you can have 5 different groups or species of warblers, okay? So we have some that live at the top of the tree, some that live in the middle, some that live just on the edges of the tree, some that live more in the middle of the tree, and then some that live very low on the tree. And this partitions those resources. And so each of the warblers are still going to be able to get their nutrients that they need and get the home that they need, okay? Probably not nutrients, but more the houses, the environment for their habitat, okay? So now let's go back to competition. And so here is an example of 2 paramecium in a laboratory setting. So when they grow separately, both species can grow very effectively within a population. P. caudatum replicates easily in everything within in the environment. P. aurelia, so these are both paramecium. Aurelia grows well. But when we put them together, P. aurelia is going to outcompete P. caudatum. And so the number of P. caudatum actually decreases in the presence of P. aurelia. And here's another competition between barnacles. And this also shows resource partitioning. So in the presence, so thalamus and balanus are 2 types of barnacles. And they can both live in these 2 areas. But when they live together, they tend to compete with each other. And so they have partitioned the environment to where thalamus lives high up, where you have water sometimes, but not all the time. And Balanus lives low, where you have water almost all the time, unless it's very low tide, right? But there is an area where they still will compete with each other. That's this small area of competition. So they also partition. And then we talked about partitioning here. So I'm going to go right to the next page. The next thing is predation. So predation occurs when one organism uses another organism as prey. So this is a predator-prey population dynamic. And when you have this type of dynamic, predator and prey keep the opposite in check. So if there's too many predators, then the prey population starts to diminish, and that causes predators to not have enough food, and so they will starve, they will go hungry, or they will have to leave the environment. And this decreases the number of predators, which allows an increase in the amount of prey, which then allows more predators again. So do you see how that kind of, the predators keep the prey in check, and the prey actually population keeps the predators in check. So let's look at that. Here we see the lynx cat and the snowshoe hare. This is a beautiful picture of predator and prey, or a beautiful example of predator and prey cycling. So anytime we have an increase in the snowshoe hare, so like this red line goes up, this is during a decrease in the number of lynx that we have. But as snowshoe hare numbers increase, then we have predator increase. So when the predators increase, snowshoe hare numbers decrease, which causes the predator population to decrease. And so they kind of follow this cycling together. And there you can see that population, which I just talked about. So I'm going to stop here, and then we'll talk about some defenses that some organisms have developed in defense of predators. Bye.